In this next section, we look at the work energy theorem. So this is section 2, lesson 4. The crate shown is on a smooth sheet of ice. It's frictionless. Any work done on pushing the box is all considered useful work, since none of the energy is wasted in overcoming friction between the surface of the ice and the box. So as the child pushes the box, all the work is converted into energy of motion. So none of the work is used to overcome friction. So it's all used to move forward. When work is done on a perfectly frictionless horizontal surface, all the work is transformed into kinetic energy of the object. So there's a couple conditions here you need to remember. It has to be frictionless, a horizontal surface, and the work has to be transformed into kinetic energy, energy of motion. So the work done equals a change in kinetic energy of the object. If we don't meet these conditions, then you can't use the work energy theorem. Example 1, Mr. Osmond uses a force of 230 newtons to push a box that has a mass of 75 kilograms, and it's at rest in the beginning, across a smooth, frictionless gym floor. So what's the acceleration of the box? So again, you have a box, 75 kilograms. It's being pushed across the gym floor, and a force of 230 newtons is applied. Well, the force involved, the overall force, since there's no friction, the force net is equal to the force applied. If there were friction, we'd have to subtract friction, but we don't have it, so our overall force is equal to 230 newtons. We also know that force is mass times acceleration. So since we know the force and you know the mass, we can find the acceleration. So the acceleration is your force divided by your mass. And your acceleration works out to 3.07 meters per second squared. And then what is the velocity of the box after 55 meters? We have V2 is what you want to find. You know V1, because you were told the box starts from rest. You have the acceleration, and that's from the last question, and which is 3.07, and you have the distance, 55 meters. So if you look back to your kinematic formulas, you find this formula here, plug in the values that you know. So your acceleration, your distance, your V1, V2 squared is 337.7. Take the square root and you have V2, which is 18 meters per second. Now from this we'll develop a formula, and it's a work energy theorem. Or even better, we can highlight that. And it's just tying together two previous formulas. We know that work is force times distance, and kinetic energy is a half mv squared. What we'll do, we'll just come down here, because we know that the work done equals a change in kinetic energy. So the work equals change in kinetic energy, E for the energy, K for kinetic. And you'll see this would change later in upcoming examples. Work is also force times distance, and your change, your kinetic energy at the end of the situation, and your kinetic energy at the beginning. And kinetic energy, well, we've seen up here, is a half mv squared, and this is your ending velocity, and half mv squared and your beginning velocity. Alright, So we'll stop there, and next video we'll pick up a couple more examples.